Says it's working, but I don't see it. Okay, now it's over here. So, thank you everyone for coming again to our Thursday Kent seminar series. Today we're having Angeli Gamez present her work on the tire designs. Not really. Where's your actual? Okay, influence of tire parameters on roadway structures. I'm going to tell you a little bit about Angeli because we've been working together for quite a while now. And the main thing I know is you came from Nevada. And that's why she's better than all the rest of you. So, good. Paying attention.
No comment.
Angeli is a PhD candidate in civil engineering under the advisement of Professor Alcadi. Her thesis is focused on quantifying the thermomechanical interaction of the truck-tire pavement interface and its impact on critical pavement responses. She completed her master's degree in civil engineering at UIUC and her bachelor's degree in civil engineering at the University of Nevada, Reno. Angeli is an active member of the Graduate Society of Women Engineers and has recently served as the director of the 2016 Women Empowered in STEM conference, hosting 160 attendees from across the country. See, I told you she's better than you. So, I'm going to stop being funny and let Angeli be serious.
Sounds good. Good afternoon, everyone. For today, I'll be sharing with you some works that we've closely collaborated with Michelin, and it's, as you see on the title, is the influence of tire parameters on roadway structures. Prior to diving into the presentation, I'd like to acknowledge the people I worked with closely in this project as well, including Professor Alcadi, Dr. Hernandez, and also Professor Ozer. So first, let me set the higher knowledge, or what's the main umbrella of what we're doing here. So first, we know that in order to design a long-lasting pavement system, we have to include some critical parameters, including materials, loading, pavement structure, and environment. And this process is widely used in any pavement design approaches. Now, for instance, in the US, we use a mechanistic empirical approach wherein we couple these two approaches. So when we talk about mechanistic, essentially we're using either analytical or semi-analytical modeling to predict pavement responses in terms of strains, stresses, or deflections. And then that is paired with an empirical domain where those responses, for instance, in terms of strains, are quantified to by means of using transfer functions to determine the amount of numbers of repetitions should the pavement fail in a specific type of distress. And in particular, for my presentation, I'll be focusing on the loading component of this wide topic, and particularly truck loading, as we know, is the governing factor in pavement design. And so, in accordance to this, we know that there's a given axle load, a tire type, and also inflation pressure that governs this truck loading. And in reality, combining these parameters, what we expect is a three-dimensional contact stress at the tire pavement interface. For the objective of this project, what we've wanted to determine are the influence of different tire design parameters on pavement loading, response, and damage, and also how current assumptions in pavement design as of now relate to this tire pavement interaction. For the methodology of this project, what we've done is consider two typical pavement structures. As you can see here are the corresponding thicknesses. So for the thin pavement, which we'll coin and we'll use throughout the presentation, it simulates a low volume road where we have a single asphalt concrete layer with 4 inches and a granular base that is 8 inches. On the other hand, for an interstate highway, we considered 3 different asphalt concrete layers. You can see here wearing surface, intermediate layer, and the binder layer, and the corresponding thicknesses, and also a granular base. And as I've said, and I pointed out, the main premise is to understand how these contact stresses, and the partnership came from Michelin because they were the ones providing these 3-dimensional contact stresses of considering different tire parameters, which we'll see later on. And in our perspective, from our group, what we can provide is how their contact stresses influences pavement damage. And also at the end of this project and at the end of this presentation, we'll show you how we take into account not necessarily the full damage of these pavement simulations, but damage potentials of these 2 pavement systems. First, I'd like to introduce the finite element model that we used for this project. And just a quick overview, a somewhat definition of the different assumptions and considerations that we addressed in our finite element model. First, we considered a dynamic implicit analysis, which means that we are considering the mass inertia and damping forces on the pavement structure as it's loaded by a truck tire. Correspondingly, the difference of these components in the tire imprint would also influence the corresponding inertia value, so that's considered. The second one is the material characterization. For the asphalt concrete, we consider it as a linear viscoelastic with a nonlinear temperature distribution throughout all those AC layers. Also, for the base layer, for the thin pavement, as I've mentioned, that simulates the low volume road, we consider a nonlinear stress-dependent material property. On the other hand, for the thick pavement, given the thickness of the 3 layers that we've put on top of the base, we deemed that it was acceptable to characterize the base for the thick pavement as a linear elastic. And as I've mentioned, we are using 3-dimensional contact stresses, again, highlighting the fact that in reality, the contact stress are non-uniform, and also not only in the tire imprint wise, but also in terms of the stress distribution in the 3 orthogonal directions. And also, we're considering contact area at the tire pavement. Additionally, we are moving that tire pavement contact stresses continuously. So essentially what we've done is we provided a linear variation upon the entry and exit of that tire contact stresses, say, over a given element. So it actually simulates as if the tire is moving smoothly over our pavement model. Additionally, we'll see this in the next slide, but just a quick definition. We used an infinite boundary element. And the main premise of this is we didn't want our pavement finite element model to be extremely large, which costs computationally, and I mean the time to do the simulation will almost take forever should we say simulate a mile-long road, and that's not really feasible. So we use these infinite boundary elements to limit the geometric domain of our model, but still simulating the far field region of the pavement structure. And lastly, we also included layer interactions. So between the AC layers, we considered fully bonded. And obviously, the interaction between the AC and the granular to the subgrade will be different. So that's also accounted for. Here's the picture of I believe this is the thick pavement model. Generally, the height of or the depth of this model is around 4.5 meters. And the planar geometry is driven by the tire type. So the dual tire assembly will have a slightly different than the wide base tire assembly. And just breaking it down, this highly dense area, the only reason that's black because pretty much as we discretize this, it's very fine. So that's why in this view, it's highly dense and it's black. We also have a transition zone here between this really fine meshing and also, as I've mentioned, the infinite boundary elements, again, to simulate that far field region. So the responses of these boundary elements will tend to 0. And I just want to share with you, so from Michelin, as I've mentioned, we would get 3-dimensional tire pavement contact area. And here's just a picture, a sample picture of the data they would send us. So essentially, each of this grid will have a data point. And I'm not going to share the details for the sake of time of this presentation, but essentially we had to manipulate, not necessarily manipulate, but prepare these data to be compatible with our pavement model. And for the numerical matrix, for this project, we have what we call the reference cases. I'll be introducing the different categories of the cases we've studied. And just for the reference case, we have the wide base tire 445 is the nominal width of the tire. Comparing that to a conventional dual tire assembly, D275, again, the nominal width is 275. And the steer tire is at the front cab of a semi-truck. And the tire is the same as a dual tire assembly, except it's just one of the dual tires. The applied load for this reference case we considered is 37.8 kilonewton, although for steer it was decreased. And these are typical values that Michelin provided us, although all these all these tires were inflated at 690. Another category we've dive into is the same tires, holding the inflation pressure at 690 kilopascal and changing the applied load from 9 to 45 kilonewtons. Now the inflation pressure, so instead of holding the inflation pressure, now we're holding the load constant, and we're inflating from 480 to 830 kilopascal. Centrifugation, I guess it's easier to explain it in terms of speeds. So they give us a normal speed, or actually not a normal speed, a low speed of 5 miles per hour and a high speed of 55 miles per hour, and that's what they mean here by the centrifugation speeds, and holding the applied load and the tire inflation pressure of the wide base and dual tire at the same level. And we also consider differential tire inflation pressure, and this is pretty important because this is a typical condition actually for tires where when they try to maintain the inflation pressure of the tire, they don't always get to the inside of the tire. So it's actually more likely for semis to have differential tire inflation pressures, and that's why we've considered it. And here are the two differential tire inflation pressures we've considered. We've also considered a high load, which to an extreme of 44.5. And if you notice here, we also brought in an older wide base tire with a nominal width of 425 millimeters. Tire size, again, the 425, 445. They've also, and I believe, I don't recall which market they're using this currently, but here what we're seeing is a 495 millimeter wide base tire. And essentially, it's the same tire, but what they've changed in the design is the number of ribs on the tire, which is designated by -8R and -9R. 555, on the other hand, this is one of their models. This is not currently sold in the market, but they wanted to see, okay, is it worth to design this tire? And now we're holding the applied load and inflation pressure constantly. And last component or category that we compared is the tire wear. And we have the reference case, which is the brand new tire, as you may think of. And then we have two stages as half or end of life, where pretty much what they've done in their model is remove some portion of the depth of their tire, as it's simulating the wear of the tire, essentially. And I do want to disclose that for the sake of time, I won't be going into all the results, but I will be going through some of the results to see how the new method that we've come up with corresponds to the final results. So first, we are going to go through the analysis of traditional point response. And the importance of this comes into going through the, say, the MEPDG methodology, where you try to take a critical point response from a pavement structure and apply that to the stresses. And then later on, I'll be introducing another method, which is not necessarily using a point response, but in a more three-dimensional domain. So with this traditional point response, as we know, we have a loaded pavement structures. We identify some critical responses. And for instance, in MEPDG, they use the tensile strain at the bottom of the AC or vertical strain on top of the subgrades. These are just some examples. And another critical response that's not necessarily it's not implemented in MEPDG, but it has been found and proven in field and also other studies, the shear strain within the layers, especially within the AC, that correlates to near surface cracking. And as I've mentioned earlier, these critical responses are input into this transfer functions to predict the distress level. And so, remembering the pavement structure we have, the FEM picture that we have, so essentially what we've done is that we've extracted different pavement response, and just to disclose, so we have here all the strains, the different directions. 1 is in the X direction, so here it's the longitudinal strain at the bottom of the AC. This is the transverse 3 which is also in the AC. The surface, and 2 is the vertical on top of the subgrade, within the subgrade, the base and also the AC. And now the shear, 2-3, AC, base, and subgrade, and we also the von Mises stresses. But for the sake of relating it back to the conventional pavement response, so for instance, what we'll use for the for a bottom-up transfer function, we may use this tensile strain at the bottom of the AC, and here we can see the difference between the reference cases of wide base tire, dual tire, and steer. So it's clear that between these 3 reference cases, there is a clear distinction, and most predominantly in the shear strain, although in MEPDG and the current pavement design, this is not used, but we do want to point out that that's again a pretty important response. And as I've mentioned, these three we can relate bottom up and top down for rutting. And as I've mentioned, this is near surface. Now, interestingly, as we moved on in this project towards the different categories, recall that we've introduced at the beginning, now we're comparing here the influence of inflation pressure with respect to a wide base tire with a 445 millimeter nominal size. So if we were to, again, if we were to try to quantify the bottom-up fatigue number of repetitions to failure, we see that, interestingly, the point response, as you almost double the inflation pressure, the difference was not that much. And to us, it didn't quite make sense because the contribution in terms of the three-dimensional distribution of the stresses is pretty important. And also, although we can quantify that the shear strain is differing once we go into the damage domain of the stresses in terms of number of repetitions, it's not going to be seen through this approach. And so what we've done instead is we started talking and we decided, well, why don't we try to quantify the pavement responses in terms of its three-dimensional domain. We're inputting a three-dimensional contact stress. Why don't we try to output a three-dimensional parameter out of it? So with this approach, just as a quick overview, as I've mentioned, the conventional pavement approach focuses on just getting a point location, a point response at a specific location, although we know that any stress, a distress nucleation is actually governed by the surrounding weakened region. And so what we wanted to do is to create this analysis domain that includes the three principal directions that are in 3 dimensions. And just as a quick schematic, so here's a sample of the vertical pressure. Just as a pictorial representation of the fact that we have a three-dimensional input, that becomes an input. The responses that we get from the simulation becomes an input into this, what we're coining as a domain analysis engine. And the nice thing with this approach that I'll be presenting to you is that from this we get a single scalar output that is a function of three-dimensional responses. So one value that is dependent on three-dimensional responses. So for the procedure, we'll walk step by step of how this new approach is done. First, recall our pavement model. And instead of using the entire domain, as we know, one, it tends to 0 at the side, and we wanted to take a look closer to the tire imprint. And so what we've done is define a subdomain. Pretty much imagine numerically we're coring this pavement structure. And generally what we do is we go 1 meter squared from the top planar view, and we go, and depending on the pavement structure, we go throughout the full depth of the layers, and 1 meter into the subgrade. So that's essentially in the subdomain. Although this is geometrically, this is not representative of what I'm saying, but this schematically is showing you how we're coring the pavement structure. So after the subdomain, each of those elements can give us a lot of information, and what we've decided to do is, so for instance here, each of those elements can be represented by different stress values, shear and also normal stresses, but that can also be represented by principal stresses as you try to rotate this cube, eliminating the shear, which is still representative of this stress state. So what we've done is we extracted the three-dimensional principal stresses and strains from the subdomain that we extracted previously. And now our next step is to calculate this PQ, and now I'll go in what this means. So P is the mean stress. As you can see here, it's just the average of the 3 principal values, and Q is what we've coined as the shear stress indicator, and also in the mechanics domain, it is also related to an effective shear stress. And so as you can see here, we apply it in the stress domain, and correspondingly the same thing in the strain domain. So we want to have a more comprehensive representation, not only in the stress, but also in the strain domain. So again, what does the p-values represent for us? As I've mentioned, it represents the stress state as a function of the mean and stress, shear stress. We saw how that is calculated by the equations we saw previously. And now, borrowing from plasticity theory, if you recall this Moore circle, we can actually correlate this into this shear stress indicator, or effective shear stress with respect to the mean stress. And so essentially we're representing this Mohr circle and having a more like Cartesian coordinate. Instead of x, y, we have p and q. And as you can see, we're still we're transferring all the important information because it's the same failure plane that can be applied, except we just changed the axes just a little bit. So from this, as I've mentioned, what we're seeing here is a critical 2D cut or cross-sectional cut along that pavement model that we have. And essentially, these cloud of points P and Q is what we're seeing here. And I'll explain more what these cloud of points mean in the next slide. But for us, it was important to build these contour plots, so a three-dimensional representation of the shear and the mean stresses along the depth and also along the width. So 0 is in the middle of the tire. So as you can see here, this is probably a wide base tire. And we're just seeing how these cloud of points are spreading in the shear and the mean stress domain. So just a quick check for us. Now, what's the importance of this contour plot? We realize that there are critical regions you can see here. Generally, tire edges are pretty important. And since we know that the near surface is not only influenced by high compression, but also high shear, we've decided to introduce this zone partitioning to highlight the fact that that near surface region is really important. Also, the bottom region is also important. And the remainder of the cross section. As I mentioned, the top shear surface, bottom, and then the remainder. Now, how are these limits defined? First, we use the geometry of the tire width. So depending if it's wide base, dual tire, it doesn't matter. It will follow that tire width. And generally, and also what's seen in literature is the near surface is generally within 2 inches from the edge of the tire width. So we've added that. So now these vertical limits are defined by tire width plus 2 of these x's, which is, as I've mentioned, 50 millimeters or 2 inches. Now, using the layer thickness, how do we define these horizontal limits? This is dependent on the pavement structure. So for instance, for thick pavement, I believe I have 350 millimeters, and generally high shear strain or near surface distresses shows up within 3 to 4 inches. So what I've done is as an example, the limit here that I've chosen is 100 millimeters, and that's mirrored here as you can see, and that's nicely enclosing these dominant areas. So explaining what does the point cloud mean we saw earlier on. So following this zone partitioning that we see, Zone 1, as we can see here, high compression because it's closest to the tire, and also relatively high shear. Now we move on to Zone 2, definitely higher compression than Zone 1 because it's directly underneath the tire. And because of these high shear, we observed that not only did we increase to the left towards more compression, but also high shear. Zone 3, due to the symmetry of the contact stress input, we should anticipate also the symmetry, so we saw that Zone 3 just overlapped Zone 1. Zone 4, thinking of a really simple example of a bending, so as you tend towards the center of that beam along the depth, the values of the stresses will be close to 0, so we saw that this moved inward, although there is still some levels of compression and shear. Zone 5, since it's directly, there's a little bit high shear. Zone 6 corresponds to Zone 1 and 3 symmetry, so it's also placed on top of Zone 4. Now we're moving to the tension part of that bending beam example, although it's not that simple, but just for illustration. Now Zone 7, we're moving into tension and still some values of shear. Zone 8, the highest value of tension and also shear. Compared to Zone 7, and also similarly Zone 9 overlaps with Zone 7. So this is just a pictorial representation of how these of how the point cloud, what does it mean? Now, how does this relate to pavement distresses? Although we know that we're quantifying a bulk response, and I can't tell you if this will fail in top-down cracking or rutting because we're giving you a bulk or a comprehensive parameter. But just to relate, we have identified critical zones where, for instance, the near surface or Z2, which for AC, which we can find top-down fatigue or shear and rutting. And Zone 8 we have identified to be a critical region or zone for bottom-up fatigue. And we'll use these zones later on. For subgrade and base, we've only kept, or we've only analyzed or taken into account the Zone 2, although we have all these values should we extend to more analyses. Also, we've we have an isolated study or analysis for tire edges because that tends to be a very high shear area. Now that I can comprehensively tell you how that nice PQ diagram, that cloud points, it looks nice, but how does it relate to the stresses or damage potential? What we've done is we've borrowed from mechanics this failure plane. It's called a modified Drucker-Prager cap model, and it's in the same line as a more Coulomb, but it's a different model. And oops, sorry about that. And essentially, what we wanted to do is using this three-part model. As you can see, we have the linear, we have the cap to limit the amount of compression or hydrostatic on this domain, but also transition. And so the main idea is, imagine we have the spread of clouded points within this failure plane. Since we're just doing one pass over the model, we wanted to relate the distance of each of these points to a shear failure, or to this failure plane. So essentially, this point should be penalized more than this point because it's farther from failing in compression. Although, as we know, it's a mixture of compression of normal and also shear. So in order to do that, we've come up with a method to assign weight factors depending on the minimum distance of that point to that failure plane. And the next challenge is how do we actually do that? Remembering the cloud of points, what we've done is we've changed the coordinate system from Cartesian to polar, and correspondingly remember the failure plane that we have here. Although it does extend, should I extend the axis here, you'll see that same cap model over here. And the reason for that is what we've done is going to the midpoint of each of this sector. So there are 30 because we have 6 7 different types of angle and also 6 radii values. So that's 30 different sectors partitioned by this. And what we've done is we go to the midpoint of each of these sectors, find the minimum distance to this failure plane, and whatever's inside of this failure plane gets a weight factor. So the closer you are, then the likelihood to fail, and outside is pure failure. And also the weight factors that we've assigned inside will always sum up to 1. And here's just a simple, so this is the reciprocal, so the closer it is, because it'll be. So as we can see here, for example, if D1 is less than D2, then the reciprocal obviously will be higher, 1 over, and then the weight assigned to this D1 will just be greater than W2. Another consideration that we had to perform in this study is the fact that the geometry of the model differs. And that also is the consequence also goes to the fact that the dual tire assembly will have more points than the wide base tire. So if we were just to add points, it's not a fair comparison because one has more points than the other. And what we've done here along the cross-sectional, we've used the area of each of these elements and apply this homogenizing factor relative to the total area. So then we assign this another weight, as you will. So then whatever geometry or however much meshing or partition you have within the cross-section, whether it's wide base, dual, or even different types of wide base, geometrically it will still be comparable. So I've said we are following this analysis roadmap. Now we're also applying that homogenizing factor, which is that two-dimensional geometric correction. And as you can see here, what we're seeing here, it's along the tire imprint or along the longitudinal direction, so along the contact length of the tire, these cross-section also varies. And so we've also realized that we don't only have to correct in the 2D plane of this cross-section as it changes because of the tire width and along the width, the geometry of the tire, but also along the contact length. Which, as you can see here, the values are also still pretty significantly at a high level. And so what we've done is take into account not only the PQ coordinate, so the mean and the shear stress, the polar weight to relate it back to potential damage, the homogenizing factor, the cross-sectional, And the one we saw previously, which is along the contact length, is the volumetric factor. So then what we've come up with is to have a cumulative value. As you can see here, summing all of the PQ points, applying that cross-sectional geometric factor, so along the width. Now along the third dimension, this homogenizing factor, so this is the element length along the total contact length, and the weight factor to relate it to the potential damage. So using these cumulative values, we are able to account for the three-dimensional impact of our three-dimensional contact stresses. And finally, the scalar that we'll get is what we've called the cumulative damage ratio, which is normalized to a reference case. And in our case, it'll be the dual tire assembly, since it's the most predominantly used tire configuration. And remembering that we have 4 critical zones, 2 within the AC. So within the AC is top down and rutting, so zone 2. Also zone 8 for the AC because of bottom up. For base and subgrade, we have zone 2, so that's the third one. And for the fourth one is zone 2 within within the subgrade, I'm sorry. So now that we have 4 of these critical zones, we've also reported a weighted sum value of these 4 critical zones. And the premise of the weight is to follow the highest impact of those 4 critical zones. And so we'll have one scalar value for the entire pavement structure considering these 4 critical zones. So for the results of the new domain analysis approach that we've done, and I'm not going to go through details, but I just want to quickly show you the 27 cases that we've studied. And what we see here is we see a nice decrease of these cumulative ratio in the strain and also the stress domain, and these are for the thick pavements. And correspondingly, the most influential factor as these are arranged is the highest applied load, which makes sense. And so this verifies the characteristic of the method to be able to capture these different components. And as expected, we should have the highest applied load over in this left-hand side. I also want to disclose or just share quickly with you the different 4 components. As I've mentioned, we have 4 critical zones: AZ, zone 2, Z8 within the AC. For base is the same as zone 2, and subgrade. And here what we're presenting is the thick and thin pavement simulations. We have 27 cases. And the quick thing I want to show you is, especially like focusing here on the left-hand side, it was also nice for this new domain approach to capture the fact that, so the thick pavement are the full markers. So as we anticipate, the generally thick pavements fail at near surface. As you can see here, and it's also evident throughout, but just considering these points here is easier to see, we see that the AC at the zone 2 near surface is the most influenced part of the thick pavement. That's also a nice thing that this method captures. Now on the other hand, for the thin AC, which deflects a lot as you load it with the same tire loading condition, we see that the subgrade and the base are now starting to govern. Now going to the results, what we're looking here are the weighted sum. We're comparing here the wide base tire, dual tire assembly, and the steer tire with the same inflation pressure, although the wide base and dual tire are conventionally loaded at 38 kilonewton and the steer is decreased to 30. And what we can see here also corresponds to field conditions is wide base tends to have higher damage potential than the dual and also the steer. And also one thing you may notice here is for the thick pavement, which is the green marker and the green bars, the values of the stress, E, which are these markers, the circle markers, and the stress in the stress domain, they tend to be coincidental value-wise, or very close to each other. On the other hand, for the thin pavement, it's a little bit, there's a little bit of a lag, and we attribute that to the fact that thin pavements are probably more prone to capturing the non-linearity of the problem. And that's why we see, not necessarily lag, that might be a wrong word, but there's a gap between the stress and strain domains. Now, remembering that we varied the applied load, holding the inflation pressure at 690 kilopascal, the load is varied from 9, 38, and 44 kilonewton. These left-hand side corresponds to the wide base 445 and the dual tire assembly on the right-hand side. And as we anticipate, as you increase the load, the response should also increase for both pavements. And again, capturing the fact that the thin pavement is now probably in more nonlinear domain than the thick pavement. For the tire pressure, what we're seeing here is now we're introducing the 555, which is their theoretical tire model. It's not, as I've mentioned, it's not introduced in the market, but they wanted to see how we are able, how the pavement response will result if you were to load with 555. Here we have the 445 millimeter wide base tire and the dual tire assembly. And as we can see here, as we anticipate when the tire width increases, we can anticipate that the response decreases. And as we increase the tire inflation pressure, it also increases. Recall that the pavement response at critical points that we have at the very beginning did not show a variation at all. So now this highlights the fact that the three-dimensional impact of changing the tire inflation pressure is actually pretty important in the three-dimensional domain. And interestingly, the dual tire assembly was not as significantly affected in comparison to the wide base tire. For the tire size, here what we're seeing is all wide base. We have 425, 445, 495, 8 rib, and 9 rib, and the new theoretical tire 555. And as we anticipated for both thin and thick pavements, we should get a decrease as we're increasing that tire width. Maybe? Okay. Another component that we study is the tire wear life, so comparing a new tire to half-life and end. And consistently for both pavements, we didn't see a significant difference between the three cases. Now, another interesting parameter that we saw is the differential tire inflation pressure. So we know by definition one tire will be loaded higher than the other. And so when we did that weighted sum, as you can see here, what we're comparing is the reference wide base tire, and they're all loaded at 38 kilonewtons, so the same applied load. We have the two tire inflation pressure differential here. One tire is 480, the other 690. Here we have 690 and 830, and this is the reference dual tire. So we were quite intrigued why we weren't able to capture any difference between this if previously we were able to see that inflation pressure is differing. And we went back to the contour plots, and as we can see, the left-hand side is the one with the higher inflation pressure. So 690 is loaded here, 490 is over here, 830 and 690 is over here. So first, we were able to check that at least our model is capturing this because the input, that's the given. And so what we've done is to individually capture the impact of individual tires. And so we've introduced this XSEDE, so combining half of zone 2 near surface and half of the middle D1, because we see that that is still propagating towards that region, and similarly here. So we've assigned D1 with a lower inflation pressure and D2 with a higher inflation pressure. And so here what we're seeing is XSEDE, which is the right-hand side with the lower inflation pressure. And as we can see here, as you increase that inflation pressure, we're starting to see that difference. And correspondingly for D2, with the higher inflation pressures, we also see that decrease. So we've introduced this new partitioning method to highlight that for differential, there's a different response on the left and the right-hand side part of the tire. So for some final remarks for this project, as we saw, the domain analysis is able to capture the three-dimensional impact in the stress and strain domain. And in contrast to a conventional pavement analysis, which is a point response at a critical location, the bulk ratio is able to provide a more comprehensive definition of the stress and strain domains. And what we observe is the thin pavement induced greater ratios at the same loading conditions with respect to the thick pavement. And for the 4 critical zones, I quickly pointed out that for thick pavement, we were able to capture that the AC, near surface AZ, was the most influential for interstates, and on the other hand, for low volume, the granular layer showed higher impact. And what we presented to Michelin at the end of the day is to have a baseline ranking the different components that we've compared. And they said that this was really beneficial for them to see how they were going to balance the different tire design parameters. And at the end, what we've told them is the most critical and also as anticipated is applied load, followed by the tire size, as it varies from 555 to 425 for wide base tire only. The third is the inflation pressure, and also the life of the tire, which we saw was almost close to unity for all of the values. And finally, I'd like to acknowledge, of course, our center, the Illinois Center for Transportation, for all the help that we've received. And definitely the Michelin Americas Research Company. It was a really nice iterative collaboration with them as we were trying to hone this new approach. And definitely the Extreme Science and Engineering Discovery Environment, XSEDE, is pretty much an organization that handles supercomputing within the US, and without them, I think we'd still be running cases. And with that, I'd like to open the floor for any questions. Yes?
I have a question. If you can go back one slide. So were these the parameters that also made up those 27 cases that you talked about, kind of a mix?
This only reflects the one that I presented, but I think I'm missing maybe a couple cases. But it governs. These are. Do you remember where I have those boxes that I introduced slowly? So these are the bigger umbrella categories, if you may.
Okay. So there are actually tires that have combinations of these. So is that correct? Like the cases that you modeled were actual tires that they produce? I'm just wondering, like, why would you use different tires? Do they correspond to different trucks, or like what was their design behind all of these different parameters?
Yeah. So for instance, in terms of the applied load or inflation pressure, we went with extremes so we can cover that level. In terms of the tires, they did include, I believe, 425, and Jaime may help me on this if, and also correct me if I'm wrong, but I think 425 and some of these tires are used not only in the US, also in Canada, China. So the selection of the parameters reflect their market. And 555, as I mentioned, is a new tire design that they wanted to see how it influences, although it's not out. But it's a representative of their general demographics and the key parameters that they wanted to see in terms of pavement response.
Just a clarification question, Angeli. I think you mentioned in slide 43 or 45, so you did not see the effect of difference of inflation or pressure on the stress and stress?
On the individual point strains, we weren't able to see a big variation. So if I were to input that in the transfer functions, the number of repetitions to failure won't significantly change using that point response. But in the domain analysis, we were able to capture that for wide base, if you change the inflation pressure from 480 to 830, you see that increase in damage potential.
So in domain analysis, you saw that?
Yes, we did. Yeah. The life. Why we didn't see? So for instance, one, the load and inflation pressure were similar, and what they were actually doing with the tire, they have their own tire model, and what they're essentially doing is removing elements from their tire model. So it didn't change the tire configuration or loading conditions significantly.
General question that all you did is a simulation, right? So how would you like verify those results? Do you have anything?
For the domain analysis, one of the things I think we briefly talked about, one thing that we can apply this, for instance, is Jose's SEB simulation, since he has a method to quantify the distribution along that face. So that's, but in terms of doing field testing, it's impossible to get, what I mean is a direct validation of obtaining measuring principal values is impossible. But there are tools that we can use alongside to test the applicability of this, this method.
My question is aligned with this question. Very nice work, a lot of computational work, but how do you envision the future of this work from the implementation perspective and pavement design as opposed to tire design? I know it's interest for the people who design the tire to make sure like how the tire would affect the pavement, but for a pavement design engineer perspective, the person who want to go ahead and design a pavement, a DOT engineer or a person who is working with a PPG, how do you see the future of this work to be implemented in pavement design?
Implementation has definitely a long way to go, but what this method offers is pretty much the propensity or the likelihood of this case to failure and to what extent. So let's say the cumulative ratio of the white base is 2 and the dual case is 1. So there's, and I might not be quoting my results, but I'm just giving a simple example. So that'll be twice damage potential. Another future direction that this can do is we're not simulating any damage evolution. We're just simulating the first snapshot of how do these tire parameters influence pavement stresses and are they important. And by this analysis, we are showing and quantifying that importance. A direct implementation will be a long way, but at least they will have a quick check of how these influences their tire. I mean,
you might want to consider the type of the tire that the vehicles are using and how they affect the pavement when you're designing your pavement.
I'm sorry?
Do you want to like identify what type of tires the vehicles are using and you design your pavement according to that for the implementation?
I think we should, because for instance, the white base tire project with FHWA, we proposed a couple adjustment factors to quantify the use of white base tire because market penetration wise, that's highly increasing. So in terms of the influence of tire on pavement is becoming increasing because the market penetration or the likelihood of those tires coming and actually loading our pavement is high. So it is important. As I've said, in terms of a direct application, it's not, I think it's too early, but it is important.
All right, thank you.
All right, let's thank Angeli one more time for your presentation.
Thank you.